A uniform ladder, 6 meters long and weighing 200 newtons, rests against a smooth wall. The coefficient of static friction between the ladder and the ground is 0.4, and the ladder makes a 40-degree angle with the ground. How far up the ladder can a 780 Newton person climb before the ladder begins to slip? Okay, step one, I'm just going to draw a picture. Draw it pretty big because there's going to be a lot of things to label in this picture. Okay, so got my ground, got my wall, and I've got my ladder. It's a uniform ladder, so the mass is uniformly distributed, so the center of mass is going to be the center of the ladder. It's 6 meters long, so the distance from here all the way to the end is 6 meters. It weighs 200 newtons. So that tells me that the gravitational force of the ladder is equal to 200 newtons. Okay. It rests against a smooth wall, so we're going to assume up here it's nice and smooth, there's no friction. Okay. The coefficient of static friction between the ladder and the ground, so the ladder and the ground, there we have a coefficient of static friction, and that is 0.4. So I'm going to write that down off to the side. U sub s equals 0.4. The ladder makes a 40-degree angle with the ground. So I'm going to go ahead and label this angle as 40 degrees. The ladder and the ground make the 40-degree angle. How far up the ladder can a 780 Newton person climb before the ladder begins to slip? So we don't know how far, but I'm going to put the person somewhere on the ladder, so right here for now. Okay? All right, so now we're going to go ahead and it told us about two forces because we have the 780 Newton person. So we've got the force of the person here, the gravitational force of the person, which is 780 newtons. But there are other forces that we need to label in this diagram. Okay, so first the force of the ladder. All right, we're going to put that at the center of mass of the ladder, so about halfway up. So pretend that's about halfway. I'm going to label this as 200 newtons. Okay? And since it's halfway, I'm going to go ahead right now and label that distance to that force. So the distance to the force of the ladder is halfway, because it's a uniform ladder, 3 meters. Okay? Then we've got the person. We don't know where the person's located. I drew them right here. They've got a gravitational force going down of 780 newtons as well. And we don't know their distance. That's what we're trying to find. So I'll put a question mark there. The ladder makes a 40-degree angle with the ground. Okay, so just because we're in the rotational part, we're probably going to be using that. Let's go ahead. We did the force, we did a distance. Let's go ahead and get the angles as well. And for the first time, we're going to have some angles that aren't at 90 degrees. So to find our angle, we go from the point of rotation. Now, this ladder's not rotating, but if it were, okay, it would rotate around this bottom point. Okay, it can't swing up unless it would be attached here, and it's not attached, and it says that it's no friction up there. Okay, so if it starts to slip, it's going to slip this way out, and it's going to rotate down this way. So this will be our point of rotation. Okay, so the distance from here to the center of mass of the ladder we found was 3, and the angle we go from the point of rotation to where the force is being applied in the direction of the force. That angle is not labeled. However, gravitational force is always going to come straight down. So that's going to make a 90-degree angle with our ground. So if this is 90 and this is 40, we have a right triangle. And in any triangle, they need to add up to 180. So 180 minus 90 minus 40 leaves me with 50 degrees for this angle. Okay? Following the same exact logic, we could do the gravitational force down here, 90, 40. This must also be a 50-degree angle. Okay, so we've got all that information. Now we need to look for some of the forces that they didn't give us a value for. All right, well, at this point of rotation, we have the ladder. It's touching here, okay? Anytime you have a surface and the object's on the surface, we have a normal force. So there's a normal force. The normal force is always perpendicular to the surface. So the normal force is pointing straight up. Okay? We also have friction, static friction, and it always points the direction of opposite of movement or the way it would be moving. Okay, so it's going to slip backwards this way. So the static friction is going to be pointing to our right. All right, then what else do we have? So we've got a force here, force there, force there. Last force is the most commonly overlooked, okay? Up here, we have another contact with a surface, okay? So when there's a surface, there's an object touching the surface, we're going to have a normal force. This is actually the force of the wall, though, we're going to call it. All right, the force of the wall pushing back, okay, because we've already got one for Fn. So let's label these forces down here. So we've got normal force, which we don't know what it is. We've got static friction, which we don't know what it is. And we've got the force of the wall, and we don't know what that is. Okay, the distance to the normal force from our point of rotation is 0, which means I'm not even going to worry about the angle because torque is force times distance times the sine of the angle, but we're multiplying by 0, so it's not going to matter, okay, what the angle is. The distance to the static friction, same thing, 0. It's at the point of rotation, so I'm not going to worry about the angle. And then we've got the wall. The distance from the point of rotation to where the force applied by the wall is the entire ladder, so that is 6 meters. And then we've got the angle. Okay? Again, I go from the point of rotation down the lever arm all the way to where the force is being applied and out. So I need this angle right here. Okay, back to geometry. This is a horizontal line, so they are parallel. These are alternate interior angles, therefore this one is 40 degrees because alternate interior angles are congruent when the lines are parallel. Okay? Now, if you don't remember that, that's okay. You could think of it a different way. This is 40. We've got a big right triangle here, which means this is 50. This is 90, so that must be 40. Okay? Another way to look at it. All right. Now, we want to figure out how far the person can climb. That is a distance. So we know we're going to use torque. Okay? We know we need to use the fact that it's not rotating. So we need to use the net torque is equal to 0. Okay? And again, we know that torque is equal to the force times the distance times the sine of theta. So we do have a torque that's being created by the ladder. Okay? It would cause the ladder to rotate in a clockwise motion. So that torque would be negative. So we have a negative torque due to the ladder. Moving on over, we also have a torque due to this person, okay? And that person is going to cause the ladder to rotate in a clockwise direction. So it would be a negative torque as well. Then moving over, next up we've got the normal force. The normal force is being applied at the fulcrum, at the pivot. Therefore, there's no torque. So I'm just going to not write it in. Okay, we could put a 0 there, but save some space. Static friction, again, being applied at the point of rotation, at the pivot. So it's going to be 0 torque. Then we have the wall. That's not at the pivot. It's 6 meters away. So there is going to be a torque created by the wall. If this was the only force acting on the ladder would push back and get away from the wall and spin in a counterclockwise direction. So that is a positive torque. And these three must add up to 0. Okay, so this means I take negative force of the ladder times distance to the center mass of the ladder times the sine of the angle for the ladder plus a negative force for the person, distance to the person, sine of theta for the person, plus the force of the wall, distance to the wall, sine of theta for the wall. That all adds up to 0. Substitute in. So I have negative 200 times 3 times the sine of 50 plus negative 780 times the distance, which is what we don't know, times the sine of 50 plus the force of the wall. We don't know that one either. We don't want to have an equation where we have more than one unknown. So I'm going to stop here, and we're going to look for that force. See how we can find the force for the wall. Well, it is a force, okay? And we talked about force and translational equilibrium before. This ladder is not accelerating linearly up and down. It's not accelerating linearly left or right. So that means that it's not accelerating translationally either. So that means the net force in the x direction equals 0. It also means the net force in the y direction equals 0. So let's look at those x direction forces. I see the static friction pointing to the right, so positive, plus the wall pointing to the left, so negative. Those two are going to add up to 0. Unfortunately, I don't know either one. So let's go ahead and look at the forces in the y direction. We have a couple of forces. First, we have the normal force, which is pointing up, so it is positive. And then we also have the force from the ladder and the force from the person. And they are both pointing down, so we're going to make them negative. So negative force of the ladder plus negative force for the person. And they'll all add up to 0 because we are in translational equilibrium. We're not accelerating up or down. So the normal force is one that we do not know. So we'll leave it in there as Fn plus negative the force of the ladder, which was 200 newtons, plus negative the force of the person, which was 780 newtons, equals 0. Solve this. We get the normal force is equal to 980 newtons. Now that we have the normal force, we can use that along with the coefficient of static friction to find the force of static friction. So I'm going to do that in this little space here. So the force of static friction is equal to the coefficient of static friction multiplied by the normal force. The force of static friction is equal to 0.4 times 980 newtons. The force of static friction is 392 newtons. And now we can substitute that in up top. Static friction is pointing to the right in our diagram, so we'll leave that as positive, so 392 newtons, plus negative the force of the wall is equal to 0. Subtract 392 from both sides, divide by -1. The force acting on the ladder by the wall is 392 newtons as well. And now we can substitute that into our equation. So we have 392 newtons times the distance to the wall. So from the point of rotation to the wall is still 6 meters. Times the sine of 40 degrees. And all of that adds up to 0. Start simplifying some things. We simplify our first term here. We get negative 459 and 63 hundredths plus negative 597.5 times the distance to the person, which is what we're trying to find, plus 1,511 and 8/10. All of that adds up to 0. Combine our like terms, and we have negative 597.5 times the distance to the person, plus 1,052.2 equals 0. Subtract from both sides. Negative 597 and 5/10 times the distance to the person is equal to negative 1,052 and 2/10. Divide by negative 597.5. The distance to the person is 1.76 meters. So if the person goes any more than 1.76 meters up this 6-meter ladder, the ladder is going to slip. So that's not a very good situation. Again, we were at a 40-degree angle here, which is quite small. Typically, you have your ladder in, so it's almost vertical, okay? So that's one reason for this short distance before the ladder slips.